Thank you very much. It's a big honor to be here. I see Raghu left, but I will make it. I will make it short for him. I guess it's been a long day. I'll try not to use all the 40 minutes, so we can be short. And basically, this work started with a conversation that I had since 30 years or more with Carlangelo Riverani, and my dear friend and specialist in dynamical system. And the idea was to try to find also techniques coming from dynamical systems that can help in doing hydrodynamic limits, in particular in situations where relative entropy or other techniques that we have in probability do not work. I know that Fridun is also looking for such techniques coming from dynamical system. And also here is the idea is that 30 years ago, maybe 35, with Varadhan and Yao, we started to take Hamiltonian dynamics and put conservative noise in it and try to obtain hydrodynamic limits out of that. The idea behind is that this noise should come from some other degree of freedom that are very fast, chaotic, and that releases as noise macroscopically. But actually, we wanted to make this concrete and start with a completely deterministic system where there is an Hamiltonian system and there is also a deterministic perturbation that is chaotic, and see how it behaves and how to obtain the limit. So the problem is an old problem. How this, the heat equation, this is a general heat equation in the nonlinear case. The K is a thermal conductivity, and T is a certain profile of temperature that evolves in time following this equation. C is a specific heat function, something static, and K is the thermal conductivity. And we are more looking at this as a conservation law for the thermal energy. There is a connection with the temperature and thermal energy, and then we call dE the thermal diffusivity, which is connected to the thermal conductivity by this formula. And the idea is how this is obtained and the diffusive rescaling of space and time from Hamiltonian dynamics. Of course, this is a kind of a dream that we can have. So let's make it concrete. Consider a system of one-dimensional harmonic oscillators. What I will talk about is not related. One dimension is just for simplicity of the exposition. This is pinned, so there is a pinning potential, and there is a potential, an interaction potential, which is V, which are springs that attract to each other. So let me call E of X the energy associated to each atom. Arbitrarily, I associate to the atom X the potential energy of the left spring. And then you consider the Hamiltonian dynamics, just energy is conserved, so that means that the time derivative of the energy of each atom is the difference of two currents. You compute just the current using the Hamiltonian equation, and the current is just minus P of X, V prime, Qx plus 1 minus Qx. Then we expect, in a very general sense, that under certain condition that we don't know on the initial configuration, on the distribution, some random distribution is a configuration, and for nonlinear W and V, that you must have some behavior, some hydrodynamic limit behavior, where the energy under space-time diffusive rescaling will evolve following this heat equation, where the conductivity is related to the thermal diffusivity is related to the microscopic dynamics by the Green-Kubo formula. Green-Kubo formula, as you see, is a space-time integral of the correlation, space-time correlation of the energy current. So it's clear that there is a central limit theorem behind this. There is a space-time central limit theorem behind this. And in general, it's a nonlinear function of the energy. This is the correlation for the infinite system in equilibrium at energy E, or at temperature corresponding to that energy.
So in P, the local potential does not intervene at all?
Sorry?
W
does not intervene in the expression of the current, but intervenes in the correlations, in the dynamics. In fact, if you don't take off the W, if you take off the W, you have an unpin model, and in one dimension, you have that this quantity is infinite. You have superdiffusion. And this is another story, that you have fraction superdiffusion and so on. But this is just considered pin model. So you expect that this is finite, and every numerical simulation shows that as long even W nonlinear will give finite conductivity. But the mathematical status of this is completely zero, completely null. Even the convergence of the Green-Kubo formula is not known for deterministic dynamics. So we don't even have the transport coefficient. Then we have done a lot of work in the last years with many collaborators, that if you add energy-conserving noise, for example, you add a random flip of the velocities, then you can at least show in the general case, in the nonlinear case, that the Green-Kubo formula converge. But to prove the dynamic limit is another story, because it becomes, for the expert here, a very complicated non-gradient diffusive dynamic limit, where with a very degenerate, even with the noise, is a very difficult problem, where the technique developed by Ragu do not apply directly, because the dynamic is very degenerate. For diffusive problem, other for the energy, there are techniques developed by Varadhan, by Yao, connected to relative entropy, entropy production. But nothing of this works for energy, because relative entropy do not control energy. And this is a problem that was already clear by the people that are working on a dynamic limit from Boltzmann equation. At least not in the diffusive case. They work in the Euler scaling, but not in diffusive scaling. But for harmonic chain, if I take V and W quadratic, if I don't put any noise, it's a completely integrable system. And then we go into the generalized hydrodynamics, and I'm not going to talk about that, but of course they can also consider that. But if you put noise that conserves all the energy, then it's possible to prove the heat equation, the diffusive limit, at least in the average, not in the low large number. And this is part of what I'm going to say, but this is not really our point. Our idea is that we want to obtain the hydrodynamic limit out of a completely deterministic system. And this is the system that we consider with Liverani and Canestrani. So we have a harmonic chain. And the harmonic chain, each atom actually now has 2 degrees of freedom. So Px is a vector, and Qx a vector. And you put periodic boundary condition. Then you put harmonic chain. This is just in black is the dynamics of the harmonic chain. And then you put a dynamical system. This J is just a rotation of P. And you rotate each atom, the velocity of each atom, using a chaotic dynamical system, which is, so theta, you see theta is an angle or is a point in a torus. And F is a chaotic dynamics. And this is speeded up by a parameter epsilon. And you speed up epsilon fast. So it's clear, this is creating noise. If you speed up enough fast, it should act a bit like a white noise. But the point that we don't want to take the limit as epsilon to 0 and then n after. This could be done. The point is to do it together. to do it together, speeding up epsilon fast enough. So actually, it's enough to speed up epsilon n by n to the minus a. And a bigger than 6 is enough. So, of course, you can take faster thing. The interesting thing that is polynomial. It's not exponential, exponential, exponential. It's just polynomial, so it's reasonable. Maybe working more, one can improve a equal 3 or equal 4. To put a equal 1 will require different techniques than these ones that we use. So B, B is a function that has null average respect to the invariant measure of this map F. So what are these map F? This map F could be, there are two cases that we consider. One is just a simple smooth map on the interval. So some function from the circle to the circle, C infinity, which is derivative is strictly bigger than 1. So this is a standard theory in dynamical system, tells you that there exists a unique, absolutely invariant measure, and you have an exponential decay of the correlation. More interesting is if you take a torus and you take an Asimov map, for example, this one. This is more interesting because this advantage is that it's not only deterministic, but is also time reversible. So you obtain a time reversible microscopic dynamics that we start with. And also here, standard theory says that there exists a unique invariant measure, absolutely continuous, you have exponential decay of correlation. And now these are each atom has this attached, this kind of random magnetic field that is moving the velocity. Of course, moving the velocity is conserving the kinetic energy and is conserving the total energy of the system. So this is the dynamics. You have to assume that there exists for the map a periodic orbit such that the sum of B on the periodic orbit has to be different from 0. This is a technical condition that assures that in the central limit theorem associated to this map and this function B, you have a positive variance. This is the variance, and you have that if you look at the central limit theorem for B, B has 0 average respect to the equilibrium. So you have a central limit theorem that converges to a Gaussian with central Gaussian with variance gamma. And you have, of course, also the invariance principle. You converge to a Wiener process multiplied by square root of gamma. So this is the parameter gamma that we will see appear later in the diffusivity for the energy. Then, okay, let's go back to our system of particles. Now we have the position of the particles, the velocity of the particles, the momentum, the mass are equal to 1, and the angles. Each particle have this angle where these maps are acting. And on the particles, you can do what you want. You can also start with the deterministic configuration. The noise must come from the distribution of the angle. So you have to put in each some absolutely continuous distribution of the angles. And then something a little bit more than that. You have to assume that the distribution of the angle, of each angle, is a product. It's not so important, it's a product, but you need some smoothness of the density. So some gradient of the logarithm derivative bounded by constant uniformly in X. So that you need some, and that's where the noise will come in the limit from this smoothness. The rest could be even singular. Then you start, you have to set up the initial condition that you have, at least in expectation, you have this limit for the empirical distribution for some initial profile of energy. Then consider this heat equation. Now it's linear with D is this diffusion coefficient is explicitly given by this. This omega 0 was the pinning potential, the strength of the pinning potential, of the harmonic pinning potential. This is explicit. And gamma is this variance of these maps that are coming there. And then the result is that for any smoothness function, phi, in expectation, you have a convergence to the heat equation. Result, unfortunately, is only in expectation. It's an expectation because we don't have any control of higher moments. And this is a problem that bugged. I've been discussing these things with Raghu many times in many years. I have no way to control higher moments of this. Actually, we can do a little bit more than that. You can also say, well, how far you are from the limit, from the heat equation, and you can estimate this difference from the empirical distribution, the expectation empirical distribution, and the actual energy. This depends how smooth is the function phi. Remember, A is the parameter where we have speeded up the dynamical system, and this is so A is bigger than 6, so this is the case, like n to the A over 6 minus 1. So we have an estimate, actually, how close you are, which also tells you, with this, that if you look at a larger time scale, you actually converge to global equilibrium, which you expect because heat equation eventually will bring you to equilibrium. But you can also have a direct limit with that from the microscopic dynamics. OK, so this is the result. And the idea is that this dynamical system is creating a noise. There is a stochastic dynamics that is close to it. We don't want to show that our system converges to this stochastic dynamics. That will require much larger, faster scaling. We don't need that. But the idea is that this deterministic dynamics is close somehow to the stochastic dynamics, where there is a Brownian motion that rotates. There are n Brownian motions, independent, that rotates the angles of each particle.
Is there a coupling, actually? Is there a coupling? Or
no? No, they are independent. The coupling is only in the
between the two systems, the deterministic system and this one.
well, no. This is another system. now we see why we're not using a coupling. No. That will require to speed it up too much fast. We don't need that. So Stratonovich form. This is for people like Stratonovich. This is the way to write it. I mean, but calculation is better to do it in a Ito way. And if you put the same parameter gamma here, which you get there, we have exactly the same hydrodynamic limit in expectation. And this can be proved, as we will see now. So I'm not saying that we converge to that. This is just to have an idea that what is behind. The strategy of the proof is this, that you look at the evolution of the energy, of the distribution of the energy. And this the first step is the usual trivial step due to the fact that there is this conserved quantity and there is the current. So you get derivative of phi prime, and you get the expectation of the current. Now, the nice thing of this is that you have only to control second moments. You don't need to control other moments. So you only need to find the equation for the second moments. That is the joy of this system, and that's why we avoid all the problems that you will have in nonlinear systems. Then we want to show, what we need to show is not a coupling, but that these covariances integrated in time are close, in a certain sense, to the same thing of the stochastic dynamics. Then we know what the stochastic dynamic does, and we proceed like in the stochastic dynamics. OK, This seems complicated, but it's simply writing down the covariance matrix integrated in time of the position, velocity, etc. Then you compute, you put them inside the equation. This satisfies the closed system that is kind of complicated, and there is some small terms due to the fact that you have rescaled time and you have integrated. So there is a boundary, these are time boundary terms which are small. You have to estimate that they are small, but this can be done in a certain sense. Then when this somehow is a linear system, so you just go on with Fourier, you do some calculation, you work out, and you can prove that that you get something close to the expectation of the kinetic energy of each particle integrated, and you gain a second derivative here out of the Fourier analysis of this. You can do this for the stochastic, using the stochastic dynamics, and you have exactly how to close the equation. It's some work, but I mean, this is not difficult. It's basically good Fourier analysis for the. So how do you prove this? This is a generator of the random evolution. There is the Hamiltonian dynamic. This is the generator of the Hamiltonian dynamics. These are the random rotation that you have there. So for the random evolution, you just take this matrix A, this is a covariant, it's a quadratic function, and you apply the generator, you integrate in time, and then you have the boundary terms. These are the boundary terms that we were seeing in the equation before. These are small. So this will be fine for the stochastic evolution. Now for the deterministic one, this is not really true. You pay a price, and you have to see, you have to show that the difference is small. You have to write down. I save you all the calculation because will not be, it's late and will not be. But how do you control this difference? Just for the covariance, you have to check this. So the idea is that, it's a natural idea. You have the time, the diffusive time, 0 to n squared t. You divide it in small time of length h. The small time should be small enough that the particles move very little, but long enough that the dynamical system is doing their work. Of course, you need to control this. You need to control every step. First, you need to control how the central limit theorem, you block in certain time, how close you are actually to the covariance. And the other thing is that when you restart, you are conditioning on the position, so you are conditioning on the noise. And you have to be sure that you have not lost the noise, that you don't get the delta, that you can restart. You have still something absolutely continuous with the same property, and you can restart on. So you need a technique for that. And so as I said, the main difficulty is to prove that after each time step, the distribution of the angle, when conditioned the position, has still enough smoothness to ensure new convergence to the following step. So the tool to do this is called standard pair. This is a technique developed recently by Dolgo-Piat, but goes back to ideas of Sinai, like say Young, and so on. So intuitively, standard pairs are measured close to a delta function for which the deterministic dynamics still exhibit statistical properties. This is a bit more technical, but sorry. Basically, this is the construction of the standard pair. It is a kind of initial way to define certain initial distribution of the angles and of the configuration. So you have the angles are, each angle is in a certain interval ax bx that is small. And then there is, for each configuration of the angle, you have g theta is a configuration of particles, position and velocity. And this has to be on the surface, on the energy surface. So you move the angle, and you're moving the particles correspondingly in this energy surface. But they have to move very slowly. So as you move the angle, this has to move. This is the epsilon is the epsilon of the scaling. That's where it gets in here. And so you have all these parameters here, which is C bar. The energy is fixed. We are in the surface of constant energy. And you have this norm here. So this norm here, which is defined this way, has to be smaller like that. And then you have this probability measure on each angle, which have this bounds C0 and 1. So these are all parameters which are fixed. So, and there is a C0 large enough that this property is conserved by the map. This is something non-trivial that you have to prove for this interval, this chaotic map in the interval, or for this Asanov chaotic on the torus. But it's true. And the standard pair depends on all these parameters. Now you start with a standard pair, and you let it evolve with time for the interval h. So, sorry, this is the probability distribution that is induced on the initial condition by the standard pair. Now, you let it evolve a standard pair, and you don't get a standard pair, but you get a convex combination of standard pairs with the same initial parameters. So you have saved this noise. So this guarantees you that each step, you have, again, the same noise. To do this, you have to speed up by n to the 6. Maybe it could be done better, but this is what we can do there. So and this allows to control this distance in the covariance. So I save you with the details. How much time I left? Eh? 15, okay, no, I will not use it, actually it's late. I want to say something about entropy. As I said before, entropy doesn't help. Relative entropy doesn't help in this technique. But as some people are, some friends, they could maybe they're not part of the solution of the problem, they can be part of the problem. So I'm interested, and this is actually open, something that I don't know how to prove. And let me, I would like to understand how relative entropy evolves in this, and how the entropy production in this situation where there is deterministic dynamics. So you start, this is, I call it Rostari, the density of the stationary measure of the chaotic maps. So this mu equilibrium, this is the equilibrium measure for the system particles and angles. This is stay in equilibrium. So will be the equilibrium measure for our system. And let's assume that we start with initial distribution. It could be one of the standard pair, but it's not important, which has some entropy, relative entropy, respect to the equilibrium bounded by constant times n. Then, if you let it evolve in time, this deterministic system, there's nothing to do. The entropy doesn't change. It's a Gibbs entropy, so it's a trivial, there's no entropy production because you are maintaining all the information of the initial configuration. But so to see something, you have to lose information in particular on the angles. That's where the noise comes. So integrate on the angle, took the marginal over the angles, so you have a marginal deposition and the velocity, and you look at this entropy, and you have maybe this one is going to increase, or decrease, in fact. And you compute the derivative, you don't see any sign, actually. As far as, I look at it from time, I don't see why there should have a sign, the time derivative of this relative entropy. But this should be related to this entropy production of the stochastic dynamics. The stochastic dynamics had an entropy production, that is this one. So I believe that maybe this is not true for small n, but as n, this should be big N. As n goes to infinity, this quantity here should actually become negative and close to the production of entropy of the stochastic dynamics. But this is something I'm conjecturing. I don't know how to prove this. But will be interesting to understand the entropy production of the deterministic dynamics, how we compare to the one of the corresponding stochastic dynamics. Okay, to conclude, I want to say that all these results of this technique can be actually used to other problems that we have studied all these years, where we put conservative noise on Hamiltonian dynamics. For example, our paper with Yao and Raghu, the old paper of 91, with a compressible over a system of equation. I think adding this type of noise can give the ergodicity that we needed to close that, to do that, at least up to in the smooth regime, of course. In the smooth regime, I think this same result could be obtained putting such type of deterministic dynamics instead of the noise. As equilibrium fluctuation for an harmonic interaction, this is actually non-gradient dynamics, but with Makiko Sasada, we could deal with such noise also for an harmonic interaction. There we are in equilibrium, so there are no problem with entropy evolution. And then also for the diffusive fractional evolution of the energy, these are the unpinned case, also they probably can be obtained this way. So this, I think there's work for students can apply these things to all these things. And I think I can finish here. Thank you very much. And